Hey, what is up everyone? I hope all of you are doing great. And this is our second lecture for simple harmonic motion. And in this lecture, I'll be discussing about simple harmonic motion and phasor diagram and its application. Okay, and let us do a quick recap of our first lecture. In our first lecture, we have discussed about the solution of the actually how the displacement of a particle performing simple harmonic motion varies with time. So a particle will perform simple harmonic motion if the force acting on it looks something like this: F equals minus kx, where k being the SHM constant. So the acceleration looks something like this, where omega is the angular frequency, having an SI unit of radians per second. Okay, fine. And speed varies like this, where a is the amplitude. So the particle moves from a mean position to an extreme position towards right and an extreme position towards left. Basic stuff, fine. And at the end, the displacement of the particle at any time t changes something like this. So this was our general solution, where phi being the initial phase constant, and phi depends on from where the particle is starting, or what is the direction of the initial velocity of the particle. Fine. Okay, now the next one, and now see, if acceleration is minus omega square x, we can write acceleration as d2x dt2 equals minus omega square x. Let me first tell all of you that these videos are unedited. I don't have time to edit all these videos, so to make these lectures fancier, so please apologies for that. And so this is the second order differential equation which represents a simple harmonic motion. Okay, now we know that the general solution, actually this differential equation consists of infinite number of solution. Okay, and the general solution looks like this. Okay, now these solutions have some unique property. Like, for example, for this differential equation, let x1 be a solution. Okay, let x1 be a solution. Let that solution be a1 sine omega t plus pi by 3. Okay, even x2 can also be a solution, omega t plus pi by 6. Fine. Now the beauty of this differential equation is that, or the beauty of the solutions are that if x1 and x2 are the solution of this differential equation, even their linear combination will also be a solution for the same differential equation. That means if you take another solution which looks something like this one, c1x1 plus c2x2, where c1 and c2 are real coefficients, then also this x3 will be a solution of this differential equation. Okay, so basically if there is an a set of solution, infinite set of solution, and if you take any two or any n number of solutions from there and make some linear combination of all those solutions, the final answer will also be a solution. So this is the beauty of this differential equation. This or this phenomena, or this property of this solution is known as, because this is a closed form, this solution makes a closed form. That means just like the real numbers, if you take two real numbers and add those two real numbers, the final result will also be a real number, something like that. Okay, and this is only possible because the solutions are linearly independent, Okay, so this was some basic mathematical stuff. Okay, so let us go to our actual topic, that is phasor diagram. Now phasor diagram is basically the circular analogy of a simple harmonic motion. Okay, I mean, we know that when a particle performs simple harmonic motion, its motion lies between minus a to plus a, and it moves like this, to and fro motion. Okay, now we will just convert this simple harmonic motion into a circular motion. Okay, actually the particle is not performing circular motion, it's just a circular analogy to make our life easier, right? So that we can solve the question of simple harmonic motion using the concept of circular motion. Okay, as we know that the general solution is x equals a sine omega t plus phi, and we all know in trigonometry that sine function and cos function have a nice friendship with circular motion, right? I am showing you one animation. If you see this diagram, okay, and if I hold this end of the ellipse and if I rotate this end in a circular path, see what happens. Okay, see, my pencil is basically performing a circular motion, but this outer end of the ellipse is performing a simple harmonic motion, right? So this is the basic analogy of the phasor diagram. So let us build our concept for phasor diagrams. Okay, we have the general solution, which is x equals a sine omega t plus phi. Now let us draw a circle. Okay, let us draw a circle. This being passes through one of its diameter, this also passes through one of its diameter. Okay, now let the radius of this circle be equal to the amplitude of the simple harmonic motion. Okay, so radius of the circle is a. This is the x axis, this is the y axis, and this is the phase, this is the actual phase. Okay, and here in the phasor diagram, the phase is actually calculated as the angle made by the radius vector with the positive y axis in clockwise sense. Again I am repeating, this phase is calculated in the phasor diagram as the angle made by the radius vector with the positive y axis in a clockwise sense. Okay, so let us consider at t equals 0, the particle is at point P. So the radius vector, let the radius vector make an angle phi with the positive y axis in clockwise sense. After some time t, the particle reaches a point Q on the circular path, because here the particle in circular analogy rotates with an angular velocity omega. Okay, so here the angular frequency is mapped with angular velocity in the circular motion. Okay, so after some time t, the angular displacement is omega t. Fine. Now if you see that the projection of this radius vector on the x axis is this one, so this is x equals a sine omega t plus phi. Okay, so as we know that the projection of the radius vector along y axis, of course the radius vector is rotating with a constant angular velocity, fine, represents a simple harmonic motion, as I have shown you earlier. Okay, so again I am showing you that animation. So it is our, oops, sorry. Anyways, you can just skip to the previous section of the video. Fine. So now you can see that if I draw the simple harmonic motion, or the actual the motion of the particle, it moves in this way. Okay, but the corresponding circular motion happens in this way. So when particle goes from here to here in circular path, the particle moves from here to here. Okay, so this is our region 1. When the particle returns back from here to here, in circular path the motion is in this region. Okay, here. When the particle goes to the extreme left, then in circular path it is this one. and I hope you all have got the idea. This one, fine. Now let us try to solve few problems, then it will make our concept more clear. Okay. Now in my first video, or in the first lecture of SHM, we were finding the initial phase, okay, by taking out the actual boundary conditions. So for example, if t equals 0, it is given that x equals a by 2 and v is negative. So what will be the value of phi? Fine. So if we just try to represent this whole thing in a phasor, let us draw a phasor of radius a, x axis, y axis. Okay. At t equals 0, x is a by 2. So x is a by 2. So of course this line goes from a by 2, this one is a by 2. So velocity is negative. So we have two cases, either the particle will lie here or the radius vector will be like this or like this, but the velocity is negative. That means in actual SHM the particle is moving in this direction. That means we must concentrate in this region. Okay. So this is our actual radius vector, position of our radius vector. So this one is a by 2, this one is a, means this angle is 30 degree, that is pi by 6. So this angle is pi minus pi by 6, that gives you 5 pi by 6. Okay. So our initial phase is 5 pi by 6. So out of all the infinite solutions we get plus 5 pi by 6. Okay. Let us try to solve few different type of problems using phasor diagram. Suppose in our question it is given that a particle is performing SHM of amplitude A. This is the mean position. At t equals to 0, the particle is at x equals a by 2 and the velocity is negative. Okay, velocity is negative. Now the question is that time taken to reach x equals minus a by 2 for the first time. Sorry, not minus a by 2, let it us put as minus a for the first time. That means the particle starts, or our stopwatch starts from this position or this phase, and the time taken by the particle to reach from this instant to this instant. So let us draw the phasor diagram quickly. X axis, y axis. Okay. Now at t equals 0, x is a by 2. So this one is a by 2. Okay. And the particle wants to reach x equals minus a for the first time. That means in actual SHM the particle wants to go from here to here. That means in the circular path the particle should reach at this point. Fine. So the final velocity vector must reach here. That means the radius vector must rotate by this amount of angle. Now we need to find this angle. So this one is pi by 6, this one is pi by 2. So the total angular displacement is pi by 2 plus pi by 6, and that angular displacement is covered by an angular velocity of omega in time t. So 6, 3, 1, 4, 2 pi t, pi gets cancelled out to 3. So time taken is t by 3. Okay. So to reach the particle from here to here, time taken is time period by 3. Okay. Let us try to solve another one. Suppose in the question it is given that a particle performing simple harmonic motion, amplitude A, at t equals 0 the particle is at minus root 3 by 2a, velocity is in the positive direction, time taken to reach the state of maximum kinetic energy for the second time. Okay, so basically we know that the maximum kinetic energy of a particle happens at the mean position. So the particle starts moving from here, reaches the mean position, maximum kinetic energy for the first time, reaches the extreme point, comes back to the mean position, maximum kinetic energy for the second time. Okay, so let us draw the phasor quickly. These are pretty basic thing you should need to know. In YouTube people pretend to think that these are too complicated things and think themselves as some of Einstein or something after explaining these things to kids, but it's nothing like that. Okay, so at t equals 0 particle is at minus root 3 by 2, so this one is minus root 3 by 2a. Velocity is positive, that means the radius vector must remain here, because in actual circular motion, when it goes from in the clockwise sense, the particle or the projection on the x-axis goes towards right. So the radius vector a, this must be 60 degree, that is pi by 3. Okay, so the starting position of the radius vector is this one. So the particle goes to the mean position for the first time, extreme point, again mean position for the second time. Okay, so that means this whole radius vector rotates from here to here. Okay, so basically we need this angle, and this angle is pi plus pi by 3. Okay, pi plus pi by 3 due to angular velocity omega. Omega means 2 pi by t. So t equals okay 6 4 t 2 by 3 t, 3 plus 1 4 pi 2d by 3. So this is the time taken by the particle to reach its state of maximum kinetic energy for the second time. Okay, now the examiner can change its statement and to just confuse the student. Please do not worry about that. You just need to keep your fundamentals strong and just try to retrieve the data from the question. Okay, we can solve similar kind of questions using phasor diagram. Let us instead of taking one particle, let us take two particles. Okay, suppose there are two particles performing simple harmonic motion. Okay, two particles performing simple harmonic motion having the same amplitude, same angular frequency. Okay, at t equals 0 the first particle is at x equals a by 2, velocity is in the positive direction, and at t equals to 0 the second particle is at x equals minus a by 2 and velocity is in the negative direction. Okay, now the question is find time taken for collision for the first time. Okay, now these two particles are performing their each own independent simple harmonic motion. There will be some time after which they will collide if they perform this motion in the same line. Okay, now we need to find out after what time they will collide. Let us draw the phasor quickly. X axis, y axis. Okay, Now let us just draw the radial vector, position of the radial vector of both the particles. So let me name this one particle 1, this one particle 2. T equals 0, x is a by 2, a by 2, velocity is positive, that means somewhere here. Okay, so this one is particle 1, a by 2 means this one is pi by 6. Okay, now particle 2 is at x equals minus a by 2 and velocity is negative. Okay, so velocity is negative. Oh, wait a minute, let me take velocity positive. Okay, otherwise they won't meet. So if velocity is positive, the radial vector would remain in this situation. This one is pi by 6. Now both the radial vector rotates with the same angular velocity. Now after some time, the projection of these two radial vectors will lie on the same point. Okay, that means after some time the situation would look something like this. That is, both the radial vectors projection lies on the same point. Okay, so this one is 2, this one is 1, this one is pi by 6, this one is also pi by 6, because this x-axis must be the bisector line of this angle. Okay, so this whole angle is pi by 3, so this one is pi by 6 and this one will also be pi by 6. So you just need to check the angular displacement of any one of the vectors, let it be 1 or 2, doesn't matter. Let us take the radial vector 2. So how to find this one? This one is pi by 6, this one is pi by 6, so the whole angle is pi by 6 plus pi by 3, because this angle is pi by 3. Okay, so the angular displacement of the second radial vector is and it would be the same for the first one also. So pi by 6 plus pi by 3 equals 2 pi by t times t. Okay, so this is 6, 1 plus 2, 3 pi equals 2 pi by t, so 2, t equals t by 4. So after a time t by 4, both the particles will collide with each other. So these are few examples where we can use the phasor diagram. The main power of phasor diagram we can use while finding the frequencies of spring block systems or many other different cases. Okay, we'll try to do those kinds of problem in future videos. Okay, because SHM is a very vast section covering a very vast area for JEE. Okay, so I hope you all have found this video helpful and informative. Please do subscribe, like, share. Okay, dude, I need to pay my bills. Please do subscribe. Okay, so that I can monetize the channel as soon as possible. Okay, I hope you all get into a good IIT and good luck for your upcoming exams. Thank you.